Alright, this video for AP Statistics is on describing location in a distribution. So we're going to go over kind of four major topics today in this video, and hopefully that'll be really easy and it'll all make a lot of sense. Alright, the first major way to describe location in a distribution is something that we call a percentile. So a percentile is a value, and let me talk to you about what it means. So here's the definitions. We'll write it down first. First off, the pth percentile is the value. So it's an actual value from your data that has p% of data less than it. So if you take a test, your score might put you at the 60th percentile. That means that 60% of test takers scored less or lower than you. So let's kind of explain this example with a little nice little stem and leaf plot I have here. This stem and leaf plot came from test scores from 25 students. So 25 students took a test, and here's the scores. Now let's focus in on Brian. Okay, Brian is a particular student in this data range who got an 85. So Brian's individual value was, an 86. I highlighted it here. It's in bold if you could see it right there. His 86. All right, so if I want to find his percentile, I got to, first off, take how many students scored lower than him and divide that by the grand total of 25. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 kids scored lower than Brian. You could also count how many scores were at Brian or higher and then subtract. So there was 4 kids that were at Brian's 86 or higher. And then obviously you could, figure that out that there's 4 there, so that means 21 below. So anyway, 21 divided by 25 puts him at the 84th percentile. So this is 0.84, so we say this is the 84th percentile. So Brian's individual value, 86, represents the location of the 84th percentile. Now just understand that, other sets of data, the 84th percentile might be a different score. For this set of data, an 86 was the 84th percentile. Brian might get an 86 on his chemistry test in a different class, not this class, but an 86 in Brian's chemistry class might put him at the 90th percentile. It all depends on the data, obviously. So let's just do one more to kind of make sure you guys understand here. Let's talk about Jimmy real quick. Jimmy got a 72. Jimmy didn't do too hot. So what is a 72? Well, how many scores were below a 72? Well, if you look at the data, only one score was below a 72. So 1 out of 25 is 0.04. So Jimmy's at the 4th percentile. So 4% of kids scored lower than Jimmy. So percentiles are fairly easy, so make sure you understand them. Remember, this shows it's the location. A percentile is a location in the data. The 84th percentile is a specific location or position in the data. All right, next up, I just want to do a quick review of ogives. Remember, an ogive is a cumulative relative frequency chart. And here's one where we looked at several phone calls, and we looked at how long each of those phone calls was. So maybe your parents track your phone calls for a long period of time, and every phone call they track how many minutes it lasted. And here's an ogive that represents this. So we went over this before. Let's talk about, for example, this point right here. This point right here, I'll make pink, looks to be around 40 and 15. So it's 15, 40. Now that means that 40% of phone calls were under 15 minutes. So kind of like a percentile, right? So that means that 15 minutes was the 40th percentile because 40% of phone calls were lower than that particular length of 15 minutes. Now what's kind of cool here is that we learned about the median. Everybody knows that the median is the middle of your data with 50% below it. So the median is also known as the 50th percentile. Not a whole lot of people may call it that, but it is another name. So if I find the 50% mark and I come looks like straight over, and I come looks like straight down, looks like the median might be somewhere around 17 minutes, which means 50% of phone calls were underneath 17 minutes. We could also find Q1, Q1 is known as the 25th percentile. Once again, Q1 has 25% of data below it, so 25 would be somewhere right around here, and we could come straight over, straight down. The 25th percentile might be somewhere around 13 minutes. Again, just trying to approximate. And then Q3 is known as the 75th percentile. And that means that 75% of data is below it. Also means 25% is above it, but remember percentiles is below. And so the 75th percentile would be somewhere right around here. So if I kind of came straight over to here and then straight down, looks like somewhere maybe around 32 minutes. Again, I'm being kind of, approximate there. So somewhere around 32 minutes would be the 75th percentile or the third quartile. And obviously the difference between Q3 and Q1 is your IQR, or the middle 50% of the data. So pretty nice, easy explanation there for how ogives represent percentiles. Pretty cool. All right, so next up, I want to kind of focus on, just for a second here, let's kind of go back and focus on Brian for a second. Now remember, Brian got that 86. Now, what does that mean? Well, one thing we could do is we could look at this data, and this data is nice and symmetric, mound-shaped, and kind of unimodal. So everything we love here. So we'd probably want to be interested in looking at the mean of this data. And the mean of this data is 80. And the standard deviation of this data measuring the spread is 6.07. Now, somebody might say, well, how did Brian do? Well, Brian did 6 points better than the mean. So Brian was above average. But, what does that mean? Above average, is any number over the average. So Brian did 6 points better than the mean. Well, is that a lot, or is that not so? It's only a little bit. I mean, 6 points, just knowing that you're 6 points above the mean, doesn't really tell us a whole lot. You know what I mean? If the data was really, really spread out, 6 points could mean a lot. Or if the data was unspread out, 6 points could mean a little. It really all depends. So just saying that you're 6 points above the mean doesn't really tell you anything until you take the standard deviation into account. And that's the idea, is we want to be able to find a value that not only incorporates how far you are from the mean, but also represents that in terms of standard deviation as well. And believe it or not, we have that. That is called a standardized score, or a z-score. Now, we couldn't call it an s-score for standard, but s is already taken for standard deviation, so we went with the z for some reason. So the standardized score is known as a z-score, and a z-score is calculated in a really easy way. A z-score is found by taking your particular value, again, any value from the data, subtract the mean, and divide by the standard deviation. So I'm going to write standard deviation. I'm going to abbreviate that, just don't have to write it all out. So anyway, that's how you find a z-score. It's a very, very simple process. So to find Brian's z-score, we're simply going to take 86, that was Brian's score. We're going to subtract the mean of all the data, 80, and we're going to divide by the standard deviation of 6.07. Now when we do this, we get 6 divided by 6.07. So always make sure you do the subtraction first, obviously, and then divide, and we get a z-score of 0.99. Now what does a z-score tell us? First off, there's no units on a z-score. You don't put anything after it. What it does is it represents how many standard deviations you are above or below the mean. So let's write that down. Z-score measures how many standard deviations a value is above or below the mean. Now, since Brian got an 86, obviously when I subtract it, I got a positive number. And when I divide, I'm going to get a positive number. So I got positive. So Brian was 0.99 standard deviations above the mean. If Brian would have scored below the mean, then I would have subtracted and got a negative number, and he would obviously be below the mean. So the z-score is positive or negative. Now remember, we learned that a z-score is how far a typical value is from the mean. So standard deviation is how far a typical value is from the mean. So the standard deviation of 6.07 tells me that typically data is 6 points from the mean, meaning 6.07 to be exact. So meaning that if you're a little bit above 6.07, a little bit below by 6.07, you're not that weird. So we realize that Brian's score being very close to 1 standard deviation above the mean. I mean, 0.99 is very close to 1. Obviously, 6 divided by 6.07 is going to be just below 1. Tells me that he is definitely above the mean, but he's not like unusually extremely high. I mean, it fits inside of that, hey, typical data is 1 standard deviation from the mean. So in our case, 1 standard deviation is 6.07. So a standardized score is a nice way to kind of get a level playing field. It allows us to compare scores that might not come from the same set of data. So let me give you an example real quick. Let's just say that in chemistry, so I'm going to use a different color here to talk about chemistry. So let's just say on Brian's chemistry class, he also scored an 86. But the mean in his chemistry class was a 76, and the standard deviation was a 4. So how did he do in his chemistry class? Well, let's find his z-score for his chemistry class. He got an 86. He subtract the mean of 76 and divided by 4. So I'm going to go ahead and do this. So 86 minus 76 is obviously 10. 10 divided by 4 is 2.5. So in both classes, he got the same score in 86, but in chemistry his score was 2.5 standard deviations above the mean. So he wasn't just the typical 1 standard deviation from the mean. He wasn't even a typical or a somewhat typical 2 standard deviations from the mean. He was 2.5 standard deviations from the mean. So in chemistry, Brian's 86 is like a really good score. Versus in math class, he got an 86, and that was just it was a little bit above average. It was 1 standard deviation. 0.99 standard deviations above the mean. So you get how chemistry scores and math test scores are very different scores, but we can use z-scores to kind of compare them together. So z-scores allow us to express values on a common scale. Okay, I'll give you another example. You say, oh, that, you got 2 kids, but they're different ages. So who's really the bigger kid? Who's the taller of those 2 boys? Well, when they're different ages, it's not really just fair to say, well, that one's taller than that one. Well, that one's 10 and that one's 6. So to determine who's the bigger boy, you could find their z-scores. So find the z-score of the 10-year-old, subtracting the mean, the standard deviation for 10-year-olds. Find the z-score for the 6-year-old, again, subtracting the mean and dividing by the standard deviation for 6-year-olds. And then you can really see who is bigger relative to their actual age. So it kind of, again, it allows us to compare values that are seemingly uncomparable. You could do a same argument for an apple and an orange. You got apples, you got oranges. Well, which one's bigger? Well, don't just say which one is, visually bigger, because maybe one is a bigger fruit to begin with. So if you find the z-score for that apple, find the z-score for that orange, you could figure out who is really bigger, if that makes sense. So let's just kind of give you a couple more examples here real quick. Let's go back to Jimmy. If you remember Jimmy got a 72 on that math test. So Jimmy's z-score is going to be 72 minus 80 divided by 6.07. I mean, what an easy formula. So 72 divided by 80. I'm sorry, I said that wrong. 72 minus 80 divided by 6.07. So Jimmy was negative 1.32. So negative 1.32. That means that Jimmy was, the negative tells you he definitely was below the mean, and he was more than 1 standard deviation below the mean. So Jimmy, again, didn't do too hot. Remember, typical data is 1 standard deviation from the mean. Well, Jimmy was below that, so he was, didn't do so great on the test. So hopefully that's easy to kind of point out and show, and hopefully that makes a lot of sense. Let's just do one more real quick. Here's Sally. So let's say Sally got a 93 on her test. So we got her z-score would be 93 minus 86 divided by 6.07. So let's see here, 93 minus 86. I'm sorry, I did that, didn't I? I'm sorry. The average for the math test was 80, not 86. So before I messed that up. 93 minus 80 divided by 6.07 was 2.14. So again, 2.14. So she did really well. She was 2.14 standard deviations above the mean. Now, we can compare, right? Like, go back to the chemistry class where Brian got that 86, right? Brian's score in chemistry class was better than Sally's score in math class. So you think, well, 93, Sally did a lot better than Brian did in chemistry. Well, wait a minute. Z-scores allow us to compare these. And I say, well, yeah, Sally did really good in math class, but Brian's score, which was lower in chemistry, was a much better score when you start to compare it to the mean with the standard deviation of chemistry scores. So that's what z-scores are. Hopefully that makes a lot of sense and why they're very, very useful to allow us to compare data. All right, next we're going to move on to the next topic of this video, and that is transforming data. Now, what do I mean when I say we're going to transform data? So I'll give you some examples. So let's just say we have all of our data. There's our first piece, our second piece, our third piece of data, our fourth piece of data, our fifth piece of data, all the way, and those are all X's, by the way. No, they don't all look like it. All the way to our nth piece of data. Now, let's just say that this is test scores. I'm going to say, I'm going to give everybody a bonus 5 points. I'm going to add 5 to everybody's score. That's transformation. I'm transforming the data by adding 5 to everybody's score. Or maybe it's a test, and it's a really important test, and I want it to be worth double the points. So I'm going to double everybody's score. That's multiplying by 2. Again, I'm transforming the data. What I'm not talking about is saying, oh, person 4, I graded your test wrong. You got an 87 instead of an 83. That's just changing one value. I'm not talking about that. When we say transforming data, we mean changing all the data at once. You can also do this when you're converting. Maybe I'm in degrees Fahrenheit and I want to convert all of my temperatures to degrees Celsius. Or maybe I'm in meters and I want to convert all my data to feet. Again, that's transforming, converting data. All right, so first off, to understand this, I want to talk about several different types of data. The first type of data we have here are measures of center. Measures of center. Measures of center are very easy. We've already talked about these. Mean is a measure of center, and median is a measure of center. So we're going to talk about how transforming data affects measures of center. The next measure we have is measures of position, or also known as measures of location. Okay, here we're talking about Q1, that's the 25th percentile, Q3, that's the 75th percentile, or actually any percentile is considered a measure of position or a measure of location. And the third thing here is a measure of spread, or a measure of variability. Variability is just another fancy word for spread, variability. Okay, measures of variability are range, IQR, and standard deviation. Those are our measures of variability. All right, now these first two, measures of center and measure of position, actually kind of go together. I mean, if you think about it, the center of your data is a position of that data. So that's why measures of center and measures of position go together. They behave very similar. But measures of spread are very, very different. So now, when we transform data, there are two ways to transform data. Well, kind of 4, but we lump some of them together. So the first way to transform data, use a Roman numeral number 1 there, is by adding or subtracting. So again, I'm going to give everybody 5 bonus points. I'm going to add 5 to everybody's score. Or I messed up and I overgraded or something like that. I'm going to subtract 7 from everybody's score. Now, obviously, you wouldn't be happy if I did that. But anyway, you get the idea. Adding or subtracting a constant. So I'm going to add or subtract the same value, constant, the same value to everybody's score. Now, if this happens, 1 and 2, measures of center and spread, get affected. Measures of center and, measure of center and position. Oh my goodness, I messed that up. Measures of center and position change. How do they change? Well, if I'm going to add 5 to everybody's score, the mean's going to go up 5. I mean, it's pretty obvious as to why. If I'm going to add 5 to everybody's score, obvious the 40th percentile, wherever the heck the 40th percentile was, it's going to go up 5 points. The median, if it was whatever it was, it's going to go up 5 points. So the whole thing is just going to move, so measures of center and position will change. However, here's the kicker. I'm going to put this in yellow. Measures of spread stay the same. Measures of spread stay. They do not change. Now I'm going to use a little example here to kind of prove this to you. Here's data of a bunch of heights of high school students, right? And here's some particular statistics on this sample. Now, if I were to say, oh, you know what, I messed up on the counting, I got to add 2 inches to everybody's height. Imagine all of those dots just shift up to the right 2 inches. The mean is going to go from 67 to 69. Pretty easy. The median is going to go from 66 to 68. Q1, Q3, the min, the max, those are all measures of location. They're specific values that are all going to go up too. However, think about the spread. Think about the range, the max minus the min. If all I do is shift that up, I'm not actually changing the spread of my data. I'm just moving it around, but I'm not changing how it's spread out. Same thing. If everybody moves up 2 inches, my standard deviation is not going to change at all. Because remember, standard deviation is how far a typical value is from the mean. Well, I'm moving everybody up, so nobody's getting further or less far away from the mean. Everybody's staying the same. So that's why measures of spread stay the same. However, the second way we could change data, the second way we could transform data, use a Roman numeral number 2 there. The second way to transform data is to multiply or divide. And if I multiply or divide, everything changes. I'm just going to say that. Everything changes. I'm not even going to separate it. Measures of center change, measures of position change, measures of spread change. Everything changes, okay? So if I'm going to multiply everybody's score by 2, then the standard deviation gets multiplied by 2, the range gets multiplied by 2, the IQR gets multiplied by 2, percentiles get multiplied by 2, mean, median get multiplied by 2, everybody gets multiplied by 2. So again, go back to this data. If I, let's say if I convert these heights to centimeters, that's a multiplication. I'm going to have to multiply by a value to convert all of those to centimeters. Okay? To do that, everything's going to change. All the data is going to change, and they all change by the same way, by the way. They multiply by that constant, whatever it would be. So it's a very nice, easy thing to do. All right, so let me show you a typical AP test question that kind of goes over this. Let's just say that your new data is going to be 3 times your raw data, or that your raw data is like your original data, plus 7. So this is a formula that I'm going to use that changes my data, right? So I take an old data value, a raw data value, times it by 3, add 7. So let's just say that the mean was 16. What's the new mean going to be? Well, mean is a measure of center. Measure of center gets affected by multiplication, and it gets affected by addition. So I would take 3 times 16, and I would add the 7. So I would get a new mean of 55. Again, multiplication of the 3 and the addition of the 7 both affect mean. However, my standard deviation, let's just say my standard deviation was 3.4. Well, standard deviation only gets multiplied by 3. It doesn't get affected by the addition of 7. So the standard deviation of 3.4 would only get multiplied by 3, so I'd do 3.4 times 3, and I would get 10.2. I would not add the 7. So remember, the addition does not affect standard deviation, IQR, or range. Multiplication affects everybody. So keep that in mind when you're transforming original or raw data to new data. Okay? So hopefully that is very simple and makes a lot of sense. We'll do some practice with that in class. All right, last thing I want to talk about is transformations and how they affect z-scores. Okay, so what does transformations have to do with z-scores? Well, transforming Brian's score to a z-score is transforming. So actually finding z-scores in and of itself is transforming, right? So if I take a score, x, and I subtract the mean, x bar, and I divide by the standard deviation, s sub x, that is transforming Brian's score of an 86 to a z-score. So what does this do to data in general? How does this affect data in general? Well, let's think about the center of data. The center of data is your mean, right? So if I were to take the mean and I would subtract the mean, so if I'm doing Brian's math class, I would take a mean of 80 and I would subtract the mean of 80 and I would divide by the standard deviation of 6.07. Now when I do this, I get 80 minus 80 is 0. 0 divided by 6.07 is 0. So let's look at this graph over here so I can explain this. Here's the test scores right here. Here they all are. Here was the mean right in the middle of 80, right? There's the mean right there. Now, if I take that mean and plug it into my z-score formula, it converts to a mean of 0. So now my data will be centered around 0 because the mean is 0 standard deviations from the mean. The mean is the mean, so obviously it's not above, it's not below, it's the same value. So the mean itself, measured as a z-score, is 0 standard deviations from the mean. Now, let's talk about how standard deviation gets affected. Remember, standard deviation doesn't get affected by addition or subtraction. So this subtraction right here in the formula doesn't matter with standard deviation. Only the division matters. So if I take 6.07 and divide by 6.07, I get 1. And that should make complete sense because remember, z-scores measure how many standard deviations you are above or below the mean. So let's just say that Brian got an 86.07 on his test. That means he was exactly 1 standard deviation above the mean because he was exactly 6.07, 1 standard deviation above the mean. So that converts. So here was Brian's 86, by the way. Look, here it is right here, right around 1. Remember, it was actually 0.99 was his z-score, but that's pretty darn close to 1. So you get the idea that when you convert to z-scores, your scale converts to a mean of 0 and a standard deviation of 1. So look here, most data falls one standard deviation from the mean. We've been saying that for a while now, ever since we learned the definition of standard deviation. Standard deviation says how far typical data falls from the mean. So look, typical data, most data does fall one standard deviation from the mean, whether it be below or above. Now, some data is outside of the mean. I'm sorry, some data is outside of that one. Some data is a little bit higher, a little bit lower, and that is true for a lot of data, but there's not a whole lot of it out there. The other thing I wanted to point out when looking at this is that notice the one thing that did stay the same is the shape. When we converted from scores to z-scores, the shape stayed exactly the same. I mean, if I took all those numbers away, the two shapes of these dot plots are identical. And that is true when you transform data. When you transform all of your data by adding, subtracting, multiplying, or dividing, your shape will never change. It might get moved around a little bit, but the overall shape of your data, whether that be skewed left, skewed right, or symmetric, is not going to change whatsoever. Okay? So hopefully that makes sense. So when we're talking about z-scores, we're talking about a center of 0 because the mean is 0 standard deviations from itself. And we're talking about a standard deviation of 1 because a standard deviation, one standard deviation for data is, well, one of those standard deviations. So again, this scale of -2, -1, 0 in the middle, 1, then 2, that's a very common scale that we could use for any set of data. Remember, this scale allows us to say, okay, in math class, Brian was 0.99 standard deviations above the mean. That was a nice job by Brian. But in chemistry class, and I'll use a different color just so it kind of stands out. In chemistry class, remember, Brian was over here. He was 2.5 standard deviations above the mean. So you could see visually, wow, Brian did a lot better in chemistry class than he did in math class, even though he got the exact same numerical value. So this is why we have to kind of learn that numerical values themselves don't really tell us a whole lot. Okay, Brian got an 86. What does that mean, though? Oh, when you make it a z-score, you really get a sense of what it means. Same thing for anything, height or weight or any numerical value. You can actually convert it to a z-score and really get an understanding of how far above the mean is it, how far below the mean is it, how typical is it. So remember, Brian's chemistry score was really, really high, 2.5. It was not very typical at all. It was extremely high. It was maybe even an outlier. So hopefully everything in this video made sense, all the way back to percentiles, ogives. Hopefully z-scores make a lot of sense. Can't tell you enough how much you got to focus on understanding z-scores. We're going to use them the rest of the year. Make sure you understand the definition of what they measure, how many standard deviations a value is above or below the mean, and also make sure you know about transforming data. Pretty easy. Adding and subtracting, only it changes measures of center and position. Multiplication changes everybody, even measures of spread. So awesome video. Hope you guys enjoyed it, and I will see you guys in class.